You are already aware that the 8085 microprocessor has got 5 flags which can be used. Their importance is appreciated when the branching is to be done. The 5 flags that are available to us are 0 flag, the sign flag, the carry flag, the auxiliary carry flag, and the parity flag. These are designated as Z flag, which is for 0, S for sign, CY for carry, AC for auxiliary carry, and P for parity. These flags are set or reset depending upon the latest arithmetic or logical operation that has been carried out and the result that is available after that. The 0 flag would be set. When I say set, this means this will become 1. The 0 flag will become 1 when after the execution of the arithmetic or logical operation, the result becomes 0. Otherwise, it will be 0. The sign flag would be set, that is, it will become 1 when after the execution of the last instruction, that is arithmetic or logical, the MSB or the most significant bit of the result becomes 1. Otherwise, it will be 0. The carry flag, that is CY flag, would be set and will become 1 when after the execution of the last instruction, a carry is generated. Otherwise, it will be 0. When I say carry, it means that after the calculation, we have a 9th bit available instead of 8 bits which were there earlier. The auxiliary carry flag is a flag which is not normally used for branching, but is used for a special type of instruction. In this case, the auxiliary carry flag is set to 1 when there is a carry that is generated from the lower nibble to the higher nibble, that is from the bit D3 to the bit D4. We have the last flag available to us, that is parity flag. This will be set to 1 when after the execution of the last instruction, that is arithmetic or logical, the number of bits, that is number of 1 bits, becomes even. Otherwise, it will be 0. We can take an example for this, that is after the execution of the instruction, if we have the result available to us as this, in which case we can count 1 bit as 4, the parity flag would be 1. These instructions or these flags are used by, as I told you earlier, by branch group of instructions, basically for jump or return or things of that type. With this as a background, we can pass over to the addressing modes which indicate to us how we are going to have access to the data as far as the operands are concerned. We have got 5 different addressing modes available to us, that is register addressing mode, the direct addressing mode, the register indirect addressing mode, the immediate addressing mode, and lastly we can say implicit addressing mode. In register addressing mode, the data which we need to be brought in to the microprocessor or for the purpose of calculation is specified in the registers which are the part of the instruction itself. For example, we have got move C, A. C and A are 2 registers which are the part of microprocessor, and the data in this case is available in A and has to be moved to register C. This instruction is a 1 byte instruction. Then we have another way of having access to the data, and that is direct addressing. In this case, the data which you want to have access to is in some memory location, and we want to move that data to the accumulator or move the data to some other location. In this case, what we are doing is we have written an instruction LDA followed by 2000 This means what? The data is available at location 2000 and it has to be brought to accumulator. Now, if you look at this code which we have written here, 2000 which is there would require 2 bytes and LDA would require 1 byte. So this becomes a 3-byte instruction. Then we have got the next type of addressing mode, that is register indirect addressing mode. In this particular type of mode, we do not refer to the memory location at which the data is available directly, but we take the help of a register pair. Normally, in order to refer to the memory location, we use register pair HL. So let us say, as we had done in the previous case, we wanted to move the data from location 2000. Let us store that 2000 in register pair HL. When I say move M comma A, this means what? This means move the contents of register A to the memory location. Now, which is that memory location? Memory location is the address which is available in register pair HL. So this is an indirect way of having access to the memory location. You can see here, this is a 1-byte instruction. In the second type of addressing mode, that is direct addressing, and the third which I have just discussed, that is register indirect addressing, you can appreciate that the number of bytes required is quite different. In the first, we required 3 bytes. In the second, we have taken 1 byte. The basic problem here is that we are using a register pair which could have been used for something else also. Then we have the next type of addressing mode, which we call as the immediate addressing mode. In this particular case, the data or the operand which we have becomes a part of the instruction. The example we have got here is MVI A comma 11H, which means that 11 has to be moved to the accumulator. In this case, the data, that is 11, would require 1 byte, MVI A would require another byte, thereby making the total requirement of this particular instruction as 2 bytes. The last type of addressing mode which we have is implicit addressing mode. In implicit addressing mode, we do not specify any register or, for that matter, any other location, because the address of the data which has to be brought is built in the instruction itself. For example, CMA, which means complement the contents of the accumulator. Now, in this case, we have not specified any register. We have not specified any memory location. We have not specified anything beyond this except the instruction itself, which automatically will pick up or will find out the location or the address where the action is to be carried out. This requires 1 byte. So looking at these different addressing modes, one can have some idea regarding the number of bytes required for implementing the instruction. With this as a background, I think we can now appreciate the role of the timing. The microprocessor is a programmable sequential device which can be paced by the clock. One cycle of the clock is what we call as the T state, which can be shown like this. The time required for completing one instruction is what we call as the instruction cycle. Each instruction cycle has got number of machine cycles. Each machine cycle is defined as the time required for having access to the memory. The number of T state in machine cycle could be from 3 to 6, and each instruction cycle may consist of up to 5 machine cycles. The first machine cycle, which is always there in any instruction, is opcode fetch. So let us look at the sequence of actions that take place in this particular machine cycle, that is the opcode fetch. And in fact, the sequence of actions which take place can be explained very nicely with the help of the timing diagram, where we can show the actions taking place in each of the clock periods. In the opcode fetch, in the first T state, we can call as T1, the microprocessor places the address on A0 to A15, which has been shown here as A8 to A15 and AD0 to AD7. On A8 to A15, the microprocessor places the high order address, and on AD0 to AD7, it places the low order address. At the same time, the ALE goes high. This ALE signal is used to demultiplex AD0, AD7 and generate the address. During the first T state, the IO/M bar goes low, thereby indicating that there's going to be an access to the memory. During the second T state, there is no change as far as A8 to A15 is concerned. As far as AD0 to AD7 is concerned, during the second T state, it initially goes into the tri-state condition. There is nothing which takes place as far as ALE is concerned. It remains low here. IO/M bar also remains low. Towards the 1/3 period of the second T state, RD bar signal goes low. This RD bar signal combined with IO/M bar signal generates a control signal which we call as memory read signal, which we have already seen earlier. The result of RD bar going low is the fact that the memory places the data on AD0, AD7, and that is what we call as the opcode. Once the opcode has been placed during the second T state, we pass over to the third T state. During the third T state, there is no change as far as A8 to A15 is concerned, practically no change as far as AD0 to AD7 is concerned, but towards the end of the T3 state, the RD bar signal goes high, thereby losing interaction with the memory, the result of which is the loss of data on AD0 to AD7, which was our opcode. And after that, it goes into the so-called tri-state condition. During the fourth T state, A8 to A15 changes the state, AD0, AD7 remains tri-stated, ALE remains low, IO/M bar remains low, RD bar goes high. There are certain cases in which the opcode fetch work would be over after the first 4 T states. In certain instructions, we might still require 2 more T states for carrying out the further action. During the fourth T state, that is T4, the instruction code, that is the opcode which has been fetched, is decoded and machine cycles are encoded if required, and the information is passed on to timing and control block, which carries out the further action. This is as far as the opcode fetch timing is concerned. You can very well appreciate the sequence in which the actions are taking place. A similar timing diagram, which we have discussed, that is of opcode fetch, is applicable as far as the memory read is concerned. So the same diagram practically could be used for memory read. The basic difference between timing diagram of memory read and opcode fetch is that the memory read would require only 3 T states rather than 4 or 6 T states as are required by opcode fetch. So in that case, what we are going to do is everything will remain same. There's no change in the signals which are going to be there. The actions which have been shown as far as T1 is concerned, they are equally applicable. There's no change at all. As far as T2 is concerned, no change. It is identical. As far as T3 is concerned, there is no change except for the fact that there is no T4 state as far as the memory read is concerned. Then the next machine cycle which we have is memory write machine cycle. In that case, we can replace this signal by WR bar. And we'll have to modify this diagram slightly, which I'll show it here itself. As far as the first T state is concerned, the actions are identical as far as AA to A15 is concerned, AD0, AD7 is concerned, and ALA is concerned, as well as IO oblique M bar is concerned. There's no change at all. But in the T2 state, in this case, the microprocessor has to place the data on the data bus, which is AD0, AD7 now. And it places the data immediately here, which I am showing in the dotted fashion. And after it has placed the data, the WR bar signal goes low. Once the WR bar signal goes low, the memory chip to which this control signal is connected, which has been generated, of course, by using IO oblique M bar and WR bar signal, becomes active, and the data which is available on AD0 to AD7 is copied onto the memory location. Towards the end of the third T state, when WR bar signal goes high, that means it becomes inactive, the data is lost. In fact, the data is lost prior to that by the microprocessor itself. It does not leave it there any further. And during this period, the data is now copied into the memory location. Towards the end of the third T state, the AD0, AD7 becomes once again tri-stated. As far as AA to A15 is concerned, there is no change. ALE remains low, IO oblique M bar remains low. The next machine cycle which is of importance to us is the IO read and IO write. The basic difference between the time diagram as far as IO read and memory read is concerned is that in the case of memory, we had IO oblique M bar going low. In case of IO read, the IO oblique M bar signal would remain high. This is the basic difference. So let's try to see what actions are going to take place as far as the IO read is concerned. So let me say that I am talking about IO read machine cycle. The action that will take place would be like this. I am showing once again the same thing with the help of dots. During the first T state, AA to A15 will have the address, which we had earlier defined as high address. AD0, AD7, which we had earlier defined as low address, would be replaced by the address only. We'll have only the address, for the simple reason that in case of IO read and IO write, we have 8-bit address available, and the same is duplicated on AA to A15 as well as AD0, AD7. So both of these buses will have the same address available. Then ALE goes high. IO oblique M bar signal would go high, indicating that now the microprocessor wants to interact with the input-output device. In case it wants to read, that is what we want to achieve here. Once the IO oblique M bar has gone high, during the second T state, the signal which we have to use here would not be WR bar, but it would be RD bar. RD bar signal combined with IO oblique M bar will generate IO R bar signal. This IO R bar signal would activate the input device. Once the device has been activated, it will place the data on AD0, AD7. Once the data is placed on AD0, AD7, from there it will be passed on to the accumulator. The next machine cycle, which is very important for us, is the IO write machine cycle, which we can say as IO W machine cycle. The basic difference between the timing diagram of IO read and IO write machine cycle is that rather than having RD bar here, we will have WR bar signal here. As far as T1 is concerned, there is no change at all. There is no change at all. A8 to A15 contain the address from where the data is to be accepted. We are talking about writes at which the data is to be written. On AD0 to AD7, we will once again have the address where we want to write the data. ALE would go high. IO oblique M bar would go high, indicating that we want to have IO related operations. Once again, in this case, during the second T state, the microprocessor will place the data immediately after the change, after replacing the address during the second T state. No further action takes place till the WR bar signal goes low. The moment the WR bar signal goes low, this is combined with IO oblique M bar to generate IO W signal or IOW, that is input output write signal. This is applied to the output device, and the data which is available on AD0 to AD7 is written on the output device. During the third T state, the WR bar signal goes high, thereby deactivating the output device, and the data which was placed by the microprocessor on AD0 to AD7 is lost, and this, that is AD0 to AD7, goes into the tri-state condition. So these 5 machine codes or the machine cycles are worth understanding and appreciating as far as the sequential operation of the microprocessor is concerned. Once we have this knowledge, we can design circuits which would require hardware interfacing and then plan for the program. So with this as the background, now we can think about how to write programs, that is to make the flowchart. Once the problem is given to the programmer, the most important aspect of solving the problem is to draw a flowchart. Flowchart is nothing but pictorial representation of the steps that are required for solving a particular problem. The blocks that are used for drawing the flowchart are: number 1, we have the start oblique stop block, which has a shape which is elliptical in nature. Since this block does 2 functions, that is to represent the start and the stop, we have to write the word start or stop depending upon the action we want it to carry out. Since this block is not unique, it is very important that we must write the word start or stop within that. The next block we have here is the input-output block. Once again, this block does not have a unique function. Since that is the case, we must write within this block either the word input or the word output, which would define the function which is to be carried out by this particular block. The input block is the one using which we accept the data or any other thing which is required as far as the execution of the program is concerned. And output block is the one which makes us finally the results available. The third block which we have is the process block. This block has a unique function, that is of processing. When we call it process, it does not mean that it has to do some processing. Actually, it involves the mathematical manipulation. All mathematical actions that are required to be carried out, they are to be written in this block. Since this is a unique function, we need not write the word process within this block. Next block we have is the decision block. Decision block is having a shape which is of the type diamond. It has got one input and may have 2 or more than 2 outputs coming out of it. Using this block, we carry out any decisions that are to be implemented. For example, if we are interested in finding out which person amongst the two has a lesser weight, we have to carry out some comparison. For carrying out that comparison, we will be using this kind of a block. Then we have a connecting block. Connecting block is a circular picture, small in nature, which is used to connect the flow which is coming from more than one direction. And it may have input as well as output signals. Then we have got predefined subprogram blocks. This is a rectangular block with 2 parallel lines drawn here. We write the name of the predefined subprogram within this area to indicate that the whole subprogram needs to be implemented or executed at the time of the actual problem solving. You have seen in all of these blocks which I have got here, I have shown certain arrows. These arrows indicate the direction of flow of the solution. In any flow chart, you will have one start block. You may have input block, you may have output block. It's not necessary. You may have input block, you may have output block. You can have process block. You can have decision block. But it will always have a stop block, at least one stop block. You can have more than one stop block also, thereby indicating that any problem which you are trying to tackle may have more than one logical solution to that particular situation. Now, we have discussed, or rather I have told you, the various functions that can be carried out by the block. That is the start, the input, the process, the decision, the connecting block, the predefined subprogram block, the output block, as well as the stop block. Now let us try to use these blocks and solve a particular problem. Let us take a very simple problem here. The problem is to accept 2 numbers. Now, let us look at this first sentence which we have got here. It says accept 2 numbers. Whenever we have to make a flow chart, the first block has to be start block. With this much information, we have written the word start, and around that I have drawn an ellipse to indicate that this is a start block. Then the first sentence says that accept 2 numbers. The moment the word accept comes, it means we have to input something to the problem. For that, we have to use the input block. So I have used input A, comma B. I am assuming that the numbers would be A and B. The second part of the problem is add these in case they are not equal. Now, this says that I have to check whether A and B are equal or not. In case they are equal, you don't have to do anything. In case they are not equal, then they have to be added together. Now, how do we find out whether they are equal or not? That can be done by comparison. That comparison is going to be on the basis of some decision. For that, we'll use the decision block, and the same has been used here. This has got one input here. That means from the start block, we move to the input block. From input block, we are moving to the decision block. You can very well appreciate here that in the start block, I have used the word start. In the input block, I have used the word input because they did not have the unique function. In the decision block, I have not written the word decision because it has a unique function. I have written here is A equal to B. That means I am trying to compare. In case A is equal to B, I will follow this path and reach this connecting block. In case A is not equal to B, I'll follow this path and come to this block, which has a unique function, that is of processing. There I say y is equal to a plus b. That means add the two numbers a and b and store the result in y. So under any circumstances, whether a is equal to b or a is not equal to b, I'll follow either this path or I'll follow this path and will reach the connecting block. Now, looking at the problem once again, the problem was accept two numbers, add these in case they are not equal. That is the end of the problem. Since it is not told to us that we want the result, so we may have the output block, we may not have output block. So in this case, I have chosen to ignore the output block, and accordingly, immediately after the connecting block, I have come to the stop block. I have used the word stop here to indicate the action which is going to be carried out by this particular block. So I think with this brief example which I have tackled here, the concept of various blocks is clear to you. Now to conclude, I have tried to explain to you the role of number systems, the concept of assembly language, the machine language. We have discussed the various instruction formats. The role of flags has also been talked about. We have also discussed the addressing mode, which are very important. Some of these topics which I have done today, you would be covering in detail in the later chapters. One of the most important things which we are going to cover in the next chapter is regarding the instruction set, and I hope in the future lectures you will be able to appreciate them.